Well, let's begin with, first, are there any questions? We're moving on this week. We've got to move a little bit quickly, as usual, blinding speed. We're covering some topics in geometrical optics for the first part of the week, and then we'll have to do chapter 32, which goes back to wave optics because it starts to involve the wave nature of light. But in this first few hours here, hour and a half, we'll think of, again, the geometrical optics, thinking only of light as a ray that's traveling through space and through materials. But I want to motivate this a little bit because it may seem kind of dry that you have lens formulas. I don't know if you've have you looked at the chapter? I hope you did. Of course, it's good for you to be a little bit ahead. Yes, I don't need that yet. I'm going to do a Gedanken experiment a la Einstein with you. Let's Gedank a little bit. Think about what do we do when we see something? For example, suppose I draw an arrow on the board here. Now, what's going on here? How do we see it? We usually don't even stop to think about this. Like, what are we seeing? What's going on? Well, as we said early in this series, we see by reflected light. That arrow is not putting out any light by itself. So what we've got these lamps here that are because we put electricity into them, putting energy in, they're somehow able to emit light, and we're seeing the reflected light. The light is coming in, it's reflecting off the white and coming out here. Now, what do you see? In fact, all of us see this arrow, right? We all see this arrow. So the light must be coming from there to me, because I see it, and to you back there, right? And you see it, and you see it. So there must be light, in fact, coming from this arrow in all directions, such that each of us sees the arrow, right? Think about it. It's really amazing that, and also think about the fact that the light that you see is going through the pupil of your eye, which is about that big. So of all the light that's coming off of this arrow, it's just going over the whole room because anybody in the room can see it. Yet all that you see is that little tiny fraction that's going through the pupil of your eye, and that's enough for you to see that arrow. I think that's remarkable. You never stop to think about these things. So, and even how does it do that? The light is going out in all directions, and if I put my hand here or a piece of paper, there is no image. If you put a piece of paper, there's no image of that arrow anywhere because the light is just going out. So somehow, inside your eye, we'll get to the eye in due course, we have here the retina with all its multitudinous rods and cones, photoreceptors. You've certainly seen that. So, of the very few rays coming from there, they're diverging outward, somehow you're getting an image of this arrow point for point. In other words, you see this point, you see this point. All of these points are actually, it turns out that it's inverted on your retina. So point for point, some ray is coming through here, and it's creating a spot of light so that some rod or cone is activated, which corresponds to the tip of the arrow. It's quite amazing. So of that tiny fraction of light, it's grabbed, or it's captured in your eye, and it's brought down to some point here. If it just kept spreading, you would have no image. And in fact, there's maybe even another ray that comes through here, and that also must contribute to the point here. And that is known as focusing the light, which your eye does very miraculously and presents a one-for-one image of point for point on your retina. And this is done with other things too, but I think the eye is quite remarkable. So if there's a point here, for example, it's also radiating in all directions. Some small fraction of those rays passes through the pupil of your eye, manages to get focused somehow, and ends up giving you another spot on another place on the retina. And it's an image of that spot that started where the light came out. I always think this is kind of amazing. All the light coming off that arrow, most of it is wasted. I think it's really kind of tragic. It's all going out and nobody sees it. Only the tiny fraction that's going through the pupil of your eye, all of our eyes, is ever used for anything. So where's all the light gone? There might be a song in there someplace. Where has the light gone? But that's what's going on. If you ever think about it, it's quite an amazing process that we do all the time. So this is a very wonderful animation that I would recommend that you look up and play with. It's online. It's in this series called PhET, that's Physics something or other, from the University of Colorado, who are very interested in education. And they have a whole series of these animations that you can interact with. This is the one on geometrical optics. You can get it and work with it. And it shows just that very idea. It doesn't have the eye here, but you can think of it also as the light coming from this. It comes in all directions, most of it wasted. Most of it just is not captured by anything. Passes through a lens. This could be the lens of your eye, and this could be your retina. And the interesting thing is, so one of the points I would make is that if you have the idea is that from one point, get all those rays, and it's imaged here by this miraculous lens. A second point, if you have a second point, say, on this arrow or pencil, see I'm moving it up and down, and you see how the light from there, most of it is wasted too, but a little bit at least is captured by the lens or your eye, and is brought to another focus here, at a different place, so that you're reproducing what was here, you're reproducing on the screen here. And now the idea of a couple of interesting things that go on, I hope we'll get to them as we go along. One thing is, if your eyesight is a little bit bad, let's go over to this. Let me get rid of, to keep it simple, 1 point. In fact, we'd even make it less. I could do the principal rays, just a few rays, the ones that actually get through your eye, say. So with a few rays, you can sort of see where it's going. Now, one of the things you can do is put a screen here. Now, this is supposed to illustrate that if you don't have the screen at the right place, you get kind of a fuzzy image. That 1 point here is imaged, the rays are imaged into kind of a sphere of blurriness. This is what happens if, for example, you have nearsightedness or farsightedness. Your lens can't focus properly. So you have to do something about that. Actually, you see you can move this screen very nicely and then bring it to focus. Or what the eye actually does. For example, we'll get into this later on, but what the eye does, it's actually able to change the shape of the lens to bring things into focus. So, for example, if your eye were faced with a situation like this, if your eye is good, I can change the radius. I need to bring the light in sharper. And the way you do that is by making the lens rounder. We'll explain why that is, and I'll show you here. Curvatures. If I make the curvature smaller, See, I'm making the lens fatter. Here I'm doing extremes. See, and you see the fatter the lens is, the sharper the bending is. So this is what your eye is doing. Let's say you were playing tennis or basketball, something like that. You see the ball over there. As it comes to you, your eyes have to stay in focus. And what's happening, your lens, there's a lens in your eye which is automatically following that and getting fatter and thinner as the thing to keep you in focus. Or if there were a camera, if this were a camera, like your cell phone cameras or whatever, what would happen is if what they do there is they move the lens forward and back, so that if, for say, you want to focus on a different, further scene, you see you get out of focus, well, it will move, the lens will move. That's what's happening in your camera. Because what you're trying to do with the camera, you're trying to take a spot of light that comes off this object, and you're trying to get it to that, the rays coming from that point to go to a particular pixel in your camera. You know, you look in the pixels, you have like 10 million pixels. Ever see these things? Well, they're tiny little elements that are light sensitive, 10 million of them. And you're trying to get the light from one point to collect by the lens and go to that point, so that you're reconstructing the light at that point. And as your subject here, which we call in the jargon of this lecture, the object moves, you see the focus is here, so the lens has to move. If you're a camera, the lens will move back and forth to bring that into focus. And then the light from that point will hit a particular pixel in your camera, and you will reconstruct the image. And if you had, I think, let's see, I wonder if they do it 2 points. Ah, nice. Oh, why not? Every time I touch it, it goes away. So if you have a second point that has a different position, it's trying to collect the light and bring it to, it's got to bring it to the corresponding position here. And then you're reconstructing the two spots that you started with, you see? So that's what the cameras do. And it's amazing to me that a thin camera, like the phone cameras, apparently there's a little motor in there that actually drives the lens back and forth. It's hard to believe that they could pack so much stuff into that camera, but I looked it up. I couldn't understand how they can do it. The other cameras, the ones where the lens pops out and you can sort of zoom in and out, you can sort of imagine the lens moving to bring things into focus. But in the thin little, that's genius. I mean, how they engineered. It's brilliant. But your eye does it a little different. See, your eye, these things, the glass in the lens here is fixed shape. And so you have to move the whole lens in and out. Your eye is even more clever. It actually changes the shape of the lens. And it doesn't move your lens in and out in your eyeball. It's a different mechanism. Very brilliant how the eye does that. That's some great engineer up there, too. So that's the story. That's why this is interesting, because this is what's going on every moment that you see anything or you're using your cameras. And I think it's worth thinking about. So I would urge you to get this and play with it. It's really amazing. You can see what happens, for example, if the refractive index, meaning this material, gets more refractive, it's going to bend light more. So let's see if that works. In other words, I'd expect the focal distance here to shorten up if I increase the refractive index, say from 1.5 to, you see where it's shortening up? Make sense? Because these things work by refraction. See, the light comes in and it's bending in the lens. It's bending in the glass, so that the more the index of refraction is high, the bigger the angle changes. So you bring it in like that. And what else do we have? Oh, well, the diameter, that's pretty boring. It's just going to make the lens bigger. It'll catch more rays. Not so interesting. But The curvature is interesting. Namely, as you see the point, well, okay, now we'll go into a little bit of detail. I just want to motivate this, that as boring as it may seem, your eyes are doing fantastic things right now. I mean, if you look at the screen, you see one thing. If you look at your neighbor, your lens is actually going to change its shape in order that you see your neighbor in focus. It's a beautiful, beautiful thing. Let me store that. And let's go into the nuts and bolts of this. What I would like to do is to, first of all, reassure you that it's not as bad as it looks. If you look in the chapter, there's tables and charts of how to handle the equations and so on. It turns out that there are some very simple rules that you can use that we have two categories of things. We have mirrors and lenses. But it turns out that the same formulas apply to both. So if you learn one and a couple of simple rules of how to deal with them, you've got both. It's sort of package deal. So like if you know electricity, you pretty much know magnetism. Because electricity, there's charges that produce fields. You put a charge in that field, you get a force. That's electricity. Magnetism, you have a different kind of charge. You have a moving charge of currents. Produce a field, you put a current in that field, you get a force. There's parallelism. Here it's beautiful also in that there's a parallelism between lenses and mirrors. So if you get one, you got them all. So in fact we will. Let's see if I can get me an arrow for future use. But both of them have what's called a focal point. They both create focus. They magnify or demagnify. And they both have special rays which help you figure out what to do. The rays are a little different in detail, but generally similar. And there are sort of sign conventions. You have to know when you speak about distance, is it a plus distance or minus distance? We have a simple rule for that. And they both create what's called real and virtual images. So there really is a very strong parallelism here. And then we will first talk about, I hope as quickly as possible, single mirrors and lenses, just like one, like I just showed you. Plane mirrors, spherical mirrors, lenses, and concave. And then I don't think we'll get to it today at all, but you can put lenses and mirrors in combinations, several of them. And actually the human eye is kind of a multiple lens because the cornea of your eye does a lot of the focusing, the refracting, and then you have within that a more movable, flexible lens, which does some fine correction. So in a way it's a multiple lens. You have a lens and a lens. And then we have other things like microscopes where you have two lenses, you have telescopes which have more than one lens. Okay. And the first distinction is that mirrors work by the law of reflection. We had the law of reflection before, right? So we know that simple thing, which is that, somebody's taking all the chalk. So mirrors work by reflection. No news there. The law of reflection. In other words, what you're going to get is light. Now, we're going to be dealing mostly with variations on spherical mirrors. So there'll be a sphere whose center is here and whose radius is, say, to here. You'll have radii like this, of course. And one issue is, so whatever happens, the law of reflection will work. Like, for example, so you see a radius strikes the surface perpendicular if it's a sphere, right? Or a circle like that. Okay, so suppose you have a ray of light coming in like this at some angle. You see, this would be the angle of incidence. This is a reflecting surface, a mirror, reflecting surface. So we have the law of reflection, which would be that the light would be reflected at equal angles. Something like that. Okay. Now, let me continue with mirrors. So what we have is the concept that if a parallel beam of light is coming in to a mirror, so in other words, light is coming in, and we speak of this, if you have the circle, and you have a line through the mirror like this, and on that line, we call that the axis of the mirror, and rays that are parallel to the axis, we call paraxial. Parallel to the axis, paraxial rays. And also, we would use the approximation that the radius is very large, and we are going to be dealing mostly with rays close to the axis. So it's going to be those kinds of rays. Of course, we're going to make some geometrical approximations that simplify when that's the case. Okay, so the first concept that we have, and it applies to mirrors and, oh, by the way, of course, we're going to say later that lenses use the law of refraction, which is a different story. But let's continue with lenses. The point is that what turns out is that if a ray comes in parallel to the axis and reflects off this surface, it reflects with an equal angle. You see, this, I haven't drawn it very well, but this is a right angle. This comes in, so the angle of incidence is this angle in here, and the angle of reflection is the angle here, and those two are equal. Now, the idea is that if this is the angle, if this is an angle, this is the same angle, and these two are equal. This is equal to this, and that's equal to that. These two angles are equal. This becomes, this thing here is a isosceles triangle, because it has two angles that are equal. That makes these two sides equal. An isosceles triangle. Now, if we were very close to the axis, I've exaggerated this enormously. If we were very close to the axis, the picture would look like a parallel ray coming in, and here is the center of the circle. The radius is this way, the normal is that way. The angle of reflection is like this. You can see if this side is equal to this side, it's very equal, very close to this being equal to this, being equal, let's say length 1, length 2, the length 1 plus length 2, both of them being equal by isosceles, is equal to the radius. The place where this passes through we call the focal point, F. And you can see that the focal point F, because L1 is equal to L2, is 2L1. And so the point where it passes through, L1 or L2, L is equal to the radius over 2. So that is that's the first rule that we have. For a spherical mirror, the light will pass through a point, parallel rays will pass through a point which is halfway half of the radius of the sphere from which this is cut. So, for example, I have here these beams of light. And let me dim the light. I hope these mirrors are not in your way. Oops, the wrong ones. Let's see. Yeah, is that better? I hope you can see that. But you see, we have parallel beams of light. There is a curvature here. This is curved inward, called concave. And you see where a parallel beam, that one reflects off here, passes through here. Another parallel beam strikes here, passes through. So this is the focal point. So the radius of that from which this is cut must be about like over here, about twice as long. It's pretty simple. That's all it is. It's just simple geometry. And there's this focal point. That's what we call the focal point. And the distance here, the distance between is called the focal length of that mirror. Okay? It's nothing complicated. It's just, this is very simple. So now, that's one kind of mirror cut from a sphere. So you have a sphere, and you cut out a piece of it, you put aluminum on one side, and it becomes a concave mirror. On the other hand, if you put reflecting material on this side, we get a different effect, namely something like this. Again, this is the law of reflection at work. The normal is this way, and we're getting the law of reflection. Light is coming in here, out here. And that's the law of reflection, because the normal must be right in the middle of that. But you see how this ray is diverging from this, and that's called a convex mirror. Flexing, vexing, convexing, flexing, try to remember something or other. It's the opposite of concave, if you will. And so here we define, this is interesting, we define the focal length here as the place from which the light seems to be coming. Can you, are you able to see anything over here? Are you okay? Okay. You see the light, here's one ray coming out, and here's the other one coming out of this one. So what we do is we project back and say, we pretend that the light is coming from here. And that, because the light actually isn't here, because it can't get, there's no light behind this mirror, we call that it's sort of a virtual image, or a virtual source here. Because we pretend that it looks like the light is coming from there. If you put your eye over here, it'll look like the light is coming from there, but there is no light behind that mirror. So that's called virtual. When there really is no light, but it looks like it's coming from there. Because your eye is accustomed to seeing things, light coming from here to there. So if it sees light coming, it doesn't know. Like, the best image of that is when you look in the mirror, you see yourself. It looks like you're over there. But you're really over here. You look and you see yourself, and the light is coming at you, and you think, that you're over there. So that's your image in the mirror is a virtual image, because it looks like the light's coming from there, but you know very well when you think about it, the light is not coming from there. It's coming from here, bouncing off the mirror, and here. We have a cute demo of that. Let me show. Okay, here's a. Can you see? There's a lamp here. Yeah. Okay, so I'm going to turn it on. Okay, now you see? Do you see a lamp lit? Okay. Can you guys over there see the lamp? Okay. All right. Now what I'm going to do is take it out. What happened? This is magic. Smoke and mirrors. Oh, smoke and mirrors is very cute. We do this in Las Vegas all the time. They usually flunk in Las Vegas because they're too drunk. But so what's really happening here? Well, there's a plate of glass here. And the glass reflects light a little bit, like 5%. So really where the lamp is over there. Let me see if I can dig up the picture here. Yeah, this is a virtual image. This is what we're doing here. See, the lamp, there is the bulb, the lighted bulb is behind here. You can't see, that's why it's hidden. And what's happening is the light is coming, some fraction of it is reflecting off here and is going out to you. Your eyes project back and think the light is that bulb back there, but it's not. It's over here. I dare not touch it. Oh, it's not so hot. See, now it's gone, right? And that's because this is equally spaced, and so this is acting like a mirror, and there's a virtual image back there, which you interpret as the real lamp. You can come and look at this later. It fools everybody all the time. Don't feel bad. So that's a virtual image. See, the light is not coming from the back bulb. It's coming from the front bulb, and using that as this is your mirror, and you project your vision back this way. It's very nice. Okay, so that's good. What do we got? A few more minutes. Oh, yes, ma'am. Beg your pardon? Is that curved? No, it isn't. It's flat, because I'm trying to not make a. I'm trying to make a. If the mirror is flat. That's a very good point. Let's go back a little bit and try to, well, here's another interpretation of that. You see, the dark lamp is here. The bright lamp is here. It sends its light, it's partially reflected off the glass. Partially, it's only partially because you can see through the glass and you can see this bulb. And then the light reflects out here and it looks like it's coming from here. So that's the interpretation of what you're seeing. It fools everybody all the time. Can't help it. And let me, on this idea that glass is 5% reflecting, in passing, you know your rear view mirror in the car? You have a light, night and day adjustment, right? You can flip it when you're driving it at night. Familiar with that? That works also by glass having a small reflectance, like 5%. So the point is that during the day, your eyes are light adapted, and you use the mirror where you have an aluminum facing here, and you have glass at a wedge shape. So during the day, the light comes in, and you let's see, what are they trying to do here? Oh, I guess. This is the daytime thing, where the light comes in, and you adjust the angle so that the light reflects off this aluminum part, the shiny metal, comes back and goes to your eye. But it's reflecting off this mirror, so you're getting 95% roughly of the light, because your eyes are bright adapted, so you want to be able to see well. But at night, if your eyes are dark adapted because you're looking at a dark road, but the guy behind you has his bright lights on, or his lights on, so that was going to be blinding. So you don't want so much light. You don't want that 95. You want like 5% of his light to falling on your eye. So what you do is you, I lost it. My dear, where are you? Oh, I think I'm going in the wrong direction. Yeah. So what you do is you flip the mirror such that now, when the light comes in from the car behind you, it reflects off the front surface, which is at a different angle, and then that light, 5%, that 5% of the light goes to your eye. The 95%, because the angle is tilted, is reflected out that way, and you don't see it. So when your eyes are dark adapted, you don't get blinded by the person behind you. It's a very clever application of plane mirrors. So now you know how that works. Very nice. Now, we have to go back a little bit, I think. Oh, no, let me go this way. Okay, so we have plane mirrors. Now, a plane, here's my point. Right at the beginning of this set of PowerPoints, which I sent to you, I try to point out that there are just a few formulas that you have to know. This one formula gives you the positioning, where you put the lenses compared, or the mirrors, compared to where your object is in order to get a focus. This is the same formula for mirrors or lenses. It applies to both. And we define the focal point as that place where parallel light, coming from, say, the tip of the arrow, coming parallel to either object, either lens element, passes through the axis. That we call the focal point. And the distance here is the focal length. Same with, we're going to see with lenses. Here you have a lens, light going parallel, passes through a lens, is refracted, bent toward the normal in this medium, it exits it, and passes through the focal point. Parallel light passes through the focal point. Now the other rays, the other things that you want to know are some other simple rays. Like one of the rays, for example, in the case of the mirror, starts, again, we have all these rays coming out in every which direction. Some of them are complicated, but some are simple. That first one is simple. It's parallel, passes through the focal point. Another one that's simple is one that strikes right at the axis, because then the angle of incidence is equal to the angle of reflection, and so you know that ray is going to come in this way, bounce off, and go here. And where those two intersect, that's where the image is going to be. So this is a very simple way of finding out where the image is going to be. So those are special rays. The same is true here. The light will go parallel, pass through the focal point. Now when in the case of the lens, you see this part of the lens is pretty much parallel. These parts here are triangular, but right in the middle, it's pretty much flat. And light will pass through a flat thing without refracting. You see, it bends toward the normal here, but it bends away from the normal here, so it's pretty much kept its same direction, at least, you see? So if it passes through plate glass, it doesn't change its direction. There's no focusing there. So that's why that ray, in the case of the lens, see, it comes through and it pretty much goes in the same direction. Maybe shifted a little bit, but that's minor. And so that where it intersects, the ray that went through the focal point, that's where the image will occur. Got that? Very simple. And they're the same. It's the same idea. You just take some simple rays. Okay. So then we define a few things, like compared to where the element is here, you have the object's distance, the distance of the object from the mirror, or the distance of the object from the lens. That's called S in our book. Other books will call it D or L or something, but S. Okay. And then you have the place where the image forms. That's the distance where, for example, this image is forming, where the lights cross again. And where, if you put a screen or your retina, you will see something. And that's the distance S prime given here, is the distance where that image forms. Then we have another concept. We have the height of the object, and then you have the height of the image. In our book, he writes minus h prime. All you really want to know is if the arrow is up, we call it plus. If the arrow is down, we'll call it minus. Likewise here, if you have a certain height upward where the arrowhead is up, when the image is formed, it'll have a certain height, and we'll call it plus if it's up, the arrowhead, and if the arrowhead is down, we'll call it minus. So we have the height of the image. And what I am suggesting to you is that try to think of these as what are called the standard, I call, this you won't find this in books, It's called the standard form. Namely, if you think of a mirror, the image that comes to my mind, anyhow, why I call it the standard form, is you have a mirror of some sort, and you put the object in front of the mirror, so the object is in front, and then you might get an image also in front. Image is also in front, S prime. So that I would call the standard mirror. And the point is, if you're trying to use this formula of 1 over S plus 1 over S prime, that is, this being S and this being S prime, is 1 over the focal length. You have to give a sign to these things. It's a plus or minus. If it's in standard form, everything is plus. And if anything is different, give it minus. That's it. Because there's a whole table of things, plus, minus, minus, plus, depending. But if it's in this form, that the object is in front, the image is in front, and you have a concave mirror. Because I think of that as a typical mirror. If anything is different from that, we'll call it minus. Okay? And that's the only thing you have to remember. You don't have to remember every little detail, every combination of front and back and concave, convex. Okay, and we'll see how that works. Next, second set of formulas. So you need something to tell you, see, the properties of this mirror. How do you get F? Well, we know one thing. We already did this for mirrors. We know that the F is equal to the radius over 2, the radius of the circle over 2. So that's true. It turns out for lenses, it's a little more complicated because, you see, your light is passing through this refracting material, which has an index of refraction. It's doing something like this. Say a ray from here. See, it's bending toward the normal, and then when it reaches here, it bends away from the normal. So you got a complicated story, and you have different radii. You could see this is a radius, and that's a radius of the lens, for example. Okay, so you need a formula that somehow takes into account I might have different radii. I could have a lens that looks like this, for example, or I could have a lens that looks like this. Anything is possible. Or I could have a lens that looks like this. So I have to somehow take into... And it turns out that the formula is not so terrible. In fact, it actually reduces to this in certain nice cases, where it's like it's 1 over f n minus 1 over the radius of the first surface. If you're coming from this direction, you have this surface minus 1 over r2. So this takes into account the refraction of the material, which you would expect. As we showed you, as the refraction changes, the focus changes. So that's that n factor. And then the radii change. I showed you that as the thing gets more spherical. In other words, actually, it's funny. As the radius gets smaller, it refracts more. That's a little bit unintuitive, but think of plate glass. What's the radius of a flat surface? It's infinite. So an infinite radius doesn't refract at all. The light goes right through. But if you have a small thing like this, it refracts even more. So the more curvy, see, the sharper it curves, the sharper it focuses. That's a little not intuitive until you think about it, and then it makes sense. Think of a plate glass, doesn't refract at all. It's just the light passes through straight. So the more bulgy you make it, the rounder you make it, the more it refracts. So get that intuitive feeling into you. That works. And the formula actually shows that as well. And the third formula, that you have to know, and this applies to lenses and mirrors, is that the magnification is the height of the image over the height of the object. That makes sense. That's a reasonable definition. It turns out by geometry that it's equal to minus the ratio of the image distance over the object distance. In other words, the further away the image is, the more time it has for the image to grow. So the bigger S prime, the bigger H prime. Can you see that? If I'm close to the lens, well, it's geometry, it turns out. So then we, in order to solve these problems, you can just use those special rays. In other words, for example, a ray that is coming parallel, reflects off this. You see here is the line from the center. So that's the radius, and the normal is like that. So this is a nicer drawing than I made. The angle of incidence with respect to that normal, to this curvy surface. Here is the angle of reflection, and it passes through the focal point. That's one ray. Then, what is this one here? This is an interesting one. This is one that passes through the focal point, and then it strikes the mirror, but you see, then it reflects parallel. That's a cute one. That's kind of nice. And in other words, these rays are reversible. If it were going this way, you would have no trouble imagining it passes through. On the other hand, the same thing is true going this way. Or with this guy here. See, he's passing through and he passes back. So that little ray is reversible. What's another good one? How about this one here? This is one that comes through and it hits the surface with an angle of incidence with respect to this axis, and so it reflects by the law of reflection, equal angle, and it passes through that way. Yeah. Okay. So those are rays that were very handy to determine the place of the image. Anything I forgot? Yes. So again, here's the sign convention for using that formula. The standard form is a concave mirror. The object is on one side. The image is on the outside the mirror. The object could be here, and the image could be behind it. That's okay. They're both on in the air side of the mirror. So everything here would be positive. In this case, anything else, for example, if you get so close to the mirror that your image is inside, that image will be, the image distance here is negative, because you see the image is behind the mirror. If it's in front of the mirror, it's a plus. If it's behind the mirror, it's minus. Or if you don't have concave, you have convex, that's negative, and it'll turn out that the image is behind the mirror too. So both this is negative, the F is negative, and S prime will be negative, because they violate the standard rules. Okay? So that's what you have to try to remember. The other thing is, well, for what it's worth, let me just show you this demo now that we've got it out here. It's just that we have two mirrors here. I have a concave. Here I have an arrow. You guys can. Okay. What does this do? Anything? Nothing. Okay. So what's happening is the light from this is coming to, well, they have two mirrors here. Let me show you what they look like. There's one that looks like this. Yeah, what is that? Okay. And one that looks like this. Now this one, can you see something? Yeah. That's like your side view mirror. You see something reduced and upright. You can actually see what you're looking at. This is your convex mirror, and it does not produce an image. Because what's happening, the light is diverging, it's bulging out, the light is diverging. But when it reaches your eye, those few rays that reach your eye grabs it and makes an image out of it. So that's what this guy is doing. This guy is actually trying to make an image, but he's making it in the wrong place, so it's blurry. That's why you can't see anything here. But I can, I think, if I get it lined up again somehow. Yeah. See, now this fellow can't make an image, but he can. If I get the place right, the image on the wall, the light is, it's this fellow here. Let's see. Not this one. Although if I put it here, you would think that maybe no, you see, all that's happening is that this one is reflecting way over on the side. And you see there's, in order for, I'm trying to create over there, the light has to converge right at the wall to make a sharp image, and then it reflects out, and you see it as though it were a real thing, because the light is coming out, just like a real thing sends out light. That real image, the light is coming in and also going out. So it looks real, but I can place it on a wall. So that's a real image. This one is creating virtual images. Okay. Let there be light.